When engineers deploy an unpredictable AI system, they typically rely on a standard safeguard, a warning label placed directly on the user interface. The operating assumption is that if developers explicitly document an algorithm's biases in a model card or a pop-up warning, the user will process that information and logically calibrate how much they rely on the system. However, cognitive research reveals a disconnect in human behavior. What a person explicitly reads on a screen rarely dictates how they implicitly react when under pressure to make a decision. This gap between reading a warning and calibrating real-time trust is known as the transparency illusion. Humans are prone to over-relying on automated decision aids. In high-stakes environments, assuming a user will adjust their reliance based solely on a text prompt introduces a significant vulnerability. Assessing human-machine trust requires a focus on involuntary physiological reactions to errors, which provide more consistent data than subjective user reports. A 2026 study by Stites and colleagues moved away from the survey approach to hunt for a strictly neurophysiological marker of trust in automation. Instead of interrupting users with subjective questionnaires, the researchers continuously monitored their brainwaves using EEG caps while they interacted with an AI system. They were looking for event-related potentials, or ERPs. These are automatic electrical reactions in the brain that are time-locked to specific stimuli. ERPs provide a continuous, multidimensional stream of data. They allow researchers to observe cognitive processing as it happens without breaking the user's concentration. Traditional self-reporting forces a state of artificial self-awareness onto the user and often conflates different definitions of trust, which can lead to inconsistent data. By tracking these microscopic electrical shifts, researchers can observe the precise moment trust is calibrated or broken, independent of the user's conscious narrative. To establish a baseline for error processing, researchers used the flanker task. Participants quickly press a button for a central target letter, ignoring distracting flankers on either side. Incongruent flankers trick the brain into incorrect pathways, forcing speed-induced errors. This chart displays neural activity recorded the exact moment participants made forced errors. The brain generates two immediate markers: the error-related negativity, ERN dip, followed by the post-error positivity, PE. Later, a distinct electrical surge appears, known as the late positive component, or LPC. These three waves, ERN, PE, and LPC, form the brain's subconscious fingerprint of error processing, providing the data needed to test what happens when a user watches a machine fail. The experiment then shifted to the observation phase. Participants stopped playing and watched a simulated machine learning algorithm perform the exact same task. To prove the participants were actively monitoring the system, researchers interspersed review trials requiring the user to log the AI's successes and failures. The researchers deployed two different models, one highly reliable at 90% accuracy and a mediocre model at 60% accuracy. While the brain still fires ERN and P waves observing AI fail, model reliability appears within the LPC. There is a significant amplitude difference. The 60% model generates a minor bump, while the 90% model triggers a sharp spike. The highly reliable model triggers a larger spike because the LPC tracks expectation violation, how much a result differs from what the brain predicted. The LPC evidence identifies trust as an active, predictive biological state that updates based on the AI's actual performance record. Trust is calibrated continuously through experience, rather than being a static attitude chosen by the user. Next, the researchers tested the industry standard of transparency. They introduced a biased AI model that was accurate at identifying the letter S, but inaccurate with the letter H. Half the participants were explicitly warned about the H bias before the task began, while the other half were given zero explanation. If transparency information influences real-time trust, the group that read the warning should show a reduced neurological shock when the AI makes an expected error. These charts compare the neural data between the group that read the warning and the group that didn't. Across both groups, the ERP waveforms are virtually identical. These overlapping waveforms demonstrate that the brain processed AI errors with the same level of expectation violation, regardless of the prior warning. Providing textual explanations of model bias completely fails to modulate real-time physiological error assessment. The brain requires proof through performance. This biological data can be compared to conscious behavioral self-reporting to see if the user's explicit opinions matched their neural signatures. After the task, users were asked to formally rate their subjective trust in the algorithm's ability to handle specific letters. This bar chart displays the subjective trust ratings collected at the end of the biased observation blocks. Both groups gave the same trust scores at the end of the block. The differences in trust were tied to the letter type, not the warning label. Both groups organically learned to trust the more reliable letter purely through watching the AI succeed and fail in real time. The data reveals that top-down instructions cannot override bottom-up experiential learning. This suggests that relying on explainability as a shortcut to human trust is flawed at both a behavioral and biological level. This data holds broad implications for the engineers designing the next generation of automated tools. Human-machine trust is derived from a user's ability to correctly anticipate how a model will perform. Biased or unpredictable systems cannot be patched by simply adding interface warning labels or model cards. In high-consequence domains like medical anomaly detection or threat screening, assuming a user will adjust their reliance based on text can lead to dangerous errors. To properly foster appropriate reliance, users must be provided with opportunities to experience the AI's boundary conditions through direct interaction. While explainability and model cards remain useful for developers, direct, observable experience is the only biological mechanism capable of calibrating human trust.